Okay, hello everyone. Today we are going to learn the drift current in great detail. So as in the lecture note, you're gonna see a p-type silicon sample. Okay, so it would be the channel region of n MOSFET or p-type region of p-n junction diode, or what else? Source or drain region of p MOSFET. Yeah. So any application using p-type silicon material can be the candidate for today's lecture. So here, a cubic shaped p-type silicon sample uh, has been shown, and now let's calculate or build up the equations for drift current. Uh, you will see the conclusion here, right? So how to get to this final, equation shape? Let's start with estimation of volume. What kind of volume? From this volume, all carriers herein, this is a p-type silicon sample, so holes, hole is the majority carrier, so all holes now cross what plane in time t. So for given time interval t, from 0 to t second, the holes within a p-type silicon sample is now crossing uh, this black colored plane. Okay, so maybe if I draw the volume that we are interested in, would be this guy. Okay, so we're gonna measure how the holes are moving at time t of 0 to t of t. Okay, so from 0 to t in time t plane, this plane, okay, all holes are now across the plane. Then we can estimate the volume, this volume. How to do that volume? Well, we need to know the lateral distance. What is this? Lateral distance, the length is, velocity, drift velocity times the time, right? T minus 0, right? So this indicates the lateral length, okay? I'm talking about this, right? And then to estimate the volume, we need to know the area, right? Area means, this length and the height. The multiplication of this height and width would become the cross-sectional area, the black colored planes area. So we can simply multiply the planes area. Then we're gonna get the volume, okay? So Vd times T times A. There we go, right? VdTA. So again, Vd indicates a drift velocity, okay? So here notice that electric field has been applied, which means voltage difference is existing in between, say, location A to location B. The voltage difference between A and B is V, and resulting in the electric field between plane A and B. Okay, and now because under the electric field, we have learned that the force is going to be applied to the all charged particles in the p-type silicon material under the electric field. So this force would cause the acceleration of these holes, and it will have its own drift velocity. Okay, so this drift velocity times t times a. Of course, depending on which guy, uh, depending on the holes, each velocity of holes, the velocity of each hole would be very different from the others. However, again, the velocity drift velocity indicates average, again, average drift velocity. Okay, so this is a drift velocity. Vd indicates the average velocity of all holes in the p-type silicon material. All right, so we have done the very first step, number 1, and now let's move on to the next one here. You can see that the same equation from step number 1 that indicates a volume, right? And take a look at the first term, P. What is P? As we have learned, the P indicates, how many holes are there per cubic centimeter. But here, the volume that we are interested in it is this guy, right? This volume. So for a given doping concentration times, or given a hole concentration times the volume that we are interested in, it gives us what? The total number of holes in the volume that we are interested in, right? So what was the volume? All holes cross plane in time t, right? So this P times volume, VDTA, is identical to what? The number of holes. The number of holes, but what kind of holes? They are crossing the plane in time t, okay? So all the holes crossing this volume, we may count how many holes have crossed this volume, okay? And the answer is P times VDTA, okay? All right, so that's done. That's all for step number 2. Now let's move on to the step number 3. Still there is the same terms, P VDTA. And what is added? Q. What is Q? Yeah, unit charge. Okay, so unit charge means coulomb per number, right? The unit the unit of unit charge indicate is coulomb per number. Well, actually, this value is 1.6 times 10 to the minus 19 coulomb, actually, per hole or per electron. But in this case, we are talking about p-type silicon. You may think of it as a coulomb per hole. Okay, so in the second step, we have estimated the total number of holes crossing the plane in time t, and now we are now multiplying unit charge value with the PVDTA, that is, which is number of holes crossing plane in time t. So this QPVDTA indicates what? The total charge, what? Crossing the plane in time t, right? So suppose that the P is, say 10, and if we multiplying unit charge times 10 means total charge coming from 10 holes, right? That kind of mechanism can be used to know the meaning of this term QPVDTA. Okay, all right. So we all done for step number 3. Now let's move on to the step number 4. What is this? QPVDTA, no T, right? No T, and T has gone. What it means is we're gonna divide this term by T, which means instead of saying in time T, from now on we're gonna say per unit time or every second. Okay, so every single second, how much charge has crossed the plane? Okay, so Q times P V D A. Okay, so that the physical meaning of this equation Q P V D A is total charge crossing the plane every second. So if I write down the unit for this sentence phrase, every second total charge. So what is the unit for this? Coulomb per second. What is this? Yeah, ampere. So QPVDA has the unit of ampere, which means QPVDA indicates the hole current, the current flow caused by holes. Okay, so this current I is most likely uh, driven by holes. Okay, and that can be written as QPVDA. Okay, and the author of the textbook said hole current per unit area. That means, current divided by area is Q times P times VD. And this guy indicates the current density. Okay, so depending on the cross-sectional area, the current value can be determined. However, the author would like to tell you the current density, the current value per unit area, how much current is flowing per unit area. So in that sense, current density is, if we would like to flow more current in MOSFET or diode, we should look for the way how to increase the current density. Okay, so here take a look at the components for current density: hole concentration and drift velocity. So you may have a have your own experience how much water is coming out from the water tap. So maybe on the wall. So here, uh, you may guess, you may have experienced how much current, water is flowing. So what kind of things would uh, decide the total amount of water? If you fully open the handle, then much more water will flow. More open means more, the very fast, much more inflow can be obtained, can be happened. So this would be corresponding to the increasing drift velocity. What about this? P means, for given cubic area, how much water droplets are included. So much more, dense water would give us more water flow. But that's not usually happened in our life. But suppose that the total number of water particles per cubic uh, per cubic centimeter, then we're gonna expect a much more water flow out of the tap. Okay. Okay, so now we're gonna end up with this equation. Current density is proportional to what? Doping concentration or hole concentration, right? And drift velocity. Now, P is governed by doping concentration. More official, more uh, technically speaking, this P is governed by net dopant concentration, so Na minus Nd in this case. But usually Na is much, much higher than Nd, so you can ignore it. And what about this, Vd? As we have learned now, there is an electric field, right? This electric field. So drift velocity is proportional to the electric field, and its coefficient of this relationship is a mu times E, mobility, right? So the current density is also governed by what? This guy is equal to mu E. Yeah, mobility. So any technology or idea to enhance the mobility in a p-type silicon material, of course definitely in n-type silicon material as well, then that would be good idea to boost up the device performance. Okay, so your boss would be very happy if you propose a new idea to boost up the mobility without any trade-off. Then that would be very perfect. But whenever you are thinking of how much current can flow and what kind of things would determine the total amount of current, always think about this current density equation, and it is very something to do with uh, carrier's concentration and drift velocity, which is very closely associated with mobility. Okay, so all the concept that we have learned, mobility, doping concentration, even in the mobility, the mobility was defined as Q times tau sub Mn divided by Mn as the risk. So effective mass, what is this? Average scattering time between two collision events, right? So these all things in microscopic events, the hole is now moving around in the silicon crystalline material, and this silicon crystalline material is going to vibrate, phonon, right? And these free carriers would hit the phonon, and phonon scattering would be happened. And this is p-type silicon material, so at some place boron is replacing the silicon, right? So this boron is ionized as being negative, so this whole holes traveling direction would be affected by this ionized impurity. So ionized impurity scattering would be happened. So all these scattering events has been merged into the concept named as mobility, right? So all the microscopic events are included in mobility, and all doping concentration stuff are summarized into the P whole concentration, and by multiplying those two terms, we're gonna obtain the whole current density. Okay, so now uh, all the materials that we have learned in lecture 1 to now are summarized in single equation. J is Q times P times VD. Okay, all right. Now, the title of this lecture slide is conductivity and resistivity. I would say this lecture note is to introduce Ohm's law. You know the Ohm's law, right? Any voltage difference is proportional to the current flow, and the coefficient is resistance. And now we're gonna see different form of the Ohm's law. So now let's take a look at this Jn drift first. What is this? In the previous slide, J whole current density is defined, whole current density by drift is defined as Q times whole current density times Vd. Okay, so now let's take a look at this guy first. Jp drift, okay, is Qp Vd. And since this is whole, there is a typo. Please fix. This should be P. Okay. So Q times P times VDP to indicate explicitly the whole is associated with this equation. Okay. Then now VDP whole drift velocity is defined as whole mobility. This is whole, right? So whole mobility times electric field. So plug in here, then we're gonna get this equation. And now let's repeat the current density equation for electron this time. So since electron has a negative charge, so instead of plus Q, I have used the minus Q. And the electron concentration and the electron's drift velocity. So minus Q times N times VdN. And now Vd drift velocity of electron is proportional to the electric field. But think about the direction. If electric field is applied from left to right, which means a plus minus voltage difference is formed, and there is electron. Uh, which way the electron is moving? Well, definitely plus anode direction. Then drift velocity, here the direction of drift velocity is quite opposite to the electric field direction. So when I'm writing down this equation, I would like to include minus a symbol, okay, mu and e. Okay, then now let's plug in this VDN here, VDN minus q, no, minus mu n e. Okay, then this minus and that minus are cancelled out, then we're gonna end up with this equation. Okay, so in previous slide I have said this is p-type silicon sample, so many holes are there. However, still minority carries electrons, so very small number of electrons exist in the p-type silicon sample. Okay, so when we are estimating the total drift current flowing in this direction, because a voltage is applied here and electric field is formed, right? So the total drift current density consists of two components, one of which is electron drift current density, the other of which is a holes drift current density is. Okay, all right, then now plug in here and there. Then you're gonna write down this equation, and this now electric field is same and common, so we can write down the equation as this shape. So Qn mu n plus Qp mu p times electric field. Here I said this slide is talking about the Ohm's law. So why Ohm's law? The equation form for the Ohm's law is V is R times I. But this equation, J drift current density, is something times electric field is also another shape of the Ohm's law. So let's understand it first. Before moving further, let's understand this concept. All the terms in this parenthesis is denoted as a sigma. So here sigma is Q n mu n plus Q p mu p. Okay, so this sigma is defined as conductivity of a semiconductor. Okay, and its 1 over sigma is defined as resistivity. You remember the resistivity in the very first slide, entitled as what is a semiconductor. We have learned that in terms of resistivity, a certain material has super high resistivity than it is, insulating material. However, if its resistivity of the other, certain material is super low, then we can claim that this is matter. However, the resistivity value is in between the insulation material and metallic material, then that material is classified as a semiconductor. So in terms of resistivity, we can classify the material into three different ones. So that resistivity is defined as 1 over sigma, and that sigma is defined and written with this equation. So take a look at each term. Electron hole concentration, that is going to be defined by Nd and Na, right? Doping, right? And what about this mobility? Mobility includes, average scattering time, and effective mass of electron and hole. Okay, so this mobility doping stuff are everything is included in the conductivity equation, and that is going to be used to classify the materials into three different ones. Okay, all right, now let's move on to the Ohm's law. So I said V is equal to resistance times I, and here current density J is defined as sigma times E. Well, actually these two equations are identical, really identical. Why is that? Let's do this. Okay, so now on the left hand side and right hand side plane, voltage V is applied, and now uh, the inflow current is measured. So V is proportional to the I. If you increase the voltage difference, you're gonna measure the higher current, and you're gonna end up with this resistance value of this sample. Well, in using a circuit symbol, it's going to be like that. Okay, so this silicon, a chunk of silicon material has its own resistance in the unit of ohm. Okay, and now uh, the lateral length is L, and this cross-sectional area is A. Let's use this two symbol. And now this material is doped with acceptors and donors. Okay, since current density J is defined as how much current is flowing per unit area. So here in the cross-section area is defined as A, so I use the A here. Okay, and what about the electric field? You know the unit of electric field, what is it? Volt per centimeter. So how much voltage difference is applied per unit length? But in this sample, it has its own length of L. Okay, so and the voltage difference is V. So in this case, the electric field applied from left to right is defined as voltage difference V divided by L. Okay, so here E is defined as V over L. Now let's plug in these two values into the equation. Then you're gonna get this equation. I over A is equal to sigma times V over L. Okay, and now let's move these two terms on the left hand side, and V is equal to what? 1 over sigma A L I. Okay, so now let's take a look at this guy. 1 over sigma is what? Resistivity. Okay, so resistivity times what? L divided by A. What is this? Resistivity means, this chunk of silicon material has its own resistivity. And L means, geometrical parameter, how long it is. And A means how wide it is. Okay, so that is defined as resistance. And actually, we're gonna study this uh, resistance here. Okay, resistance is defined as the voltage that I have applied divided by the current that I have measured. Okay, and this R is defined as resistivity times what? Length divided by cross-sectional area. In this case, this guy. But here the width is W, so this area A is WT. So that is here. Okay, so this is the resistance, and we have learned the resistivity. The unit of resistivity is ohm times centimeter. And take a look at this unit. That is centimeter, and that is area, so centimeter square. So 1 centimeter out, and here resistivity is ohm times centimeter, and the second term has a 1 over centimeter. So this 2 centimeter is going to be cancelled out in the end. The unit is ohm for this R. Okay. Okay, so now go back to this slide, and where's my note? Oh, yeah, let me write down. Okay, so now from this equation, J was I over A, and sigma E is V over L. Therefore, V is equal to 1 over sigma A L I, and that is replaced by resistivity L over A times I, and everything of these guys are resistance times I. So C, V voltage is equal to what? Resistance times current. V is IR. Yeah, there we go. So J is sigma E is another shape of Ohm's law. Okay, and what is specified terms for sigma? Doping concentration or carrier's concentration N and P, and mobility values for each carrier. Okay, so J is sigma A. Remember this equation. All right. In this slide, we're gonna study some. When we estimate the resistivity value, you don't need to calculate all all of terms, all the terms. Just because N is much higher than P in N-type material, so you can ignore this term. Okay. And what about for P-type material? Since resistivity is defined as 1 over Qp mu P plus Qn mu N, but in P-type material, hole concentration is much higher than electron concentration, so you can ignore this term. Then it can make your life much easier when estimating resistivity of P-type or N-type material. And on the left hand side, you can see that dopant density means Na or Nd, and x-axis indicates resistivity. So depending on the doping concentration, you can, by reading out the value from here, you can simply estimate the resistivity value. Okay, but here notice that this plot does not apply for what? Compensated material. What is a compensated material? Originally it was P-type, but by adding up much more arsenide or phosphorus, which is donors, then it has been inverted into the N-type material. Then this material is named as compensated semiconductor material. So in a compensated material, this plot should not be used at all. Okay, uh, this plot is only valid when estimating the resistivity for N-type P-type material, which is not fully compensated. So, simply speaking, you can simply calculate these two equations, or uh, just calculate this guy. Then you're gonna be okay. All right. And this term we have explained it already. So now let's take a look. Try to solve one example. Consider a silicon sample doped with 10 to the 16 boron. Boron is acceptor, right? So p-type. So this silicon sample is now p-type. What is its resistivity? So the acceptor concentration is 10 to the 16 per cubic centimeter, and no donors, 0, right? So Na is much higher than Nd, so this silicon sample is now p-type. So hole concentration is governed by net dopant concentration, but in this case N is 0, so Na is equal to P. Of course, all the acceptors are fully ionized at room temperature. So without any specified conditions, we're gonna assume that all the explanation, all the things are at 300 Kelvin. Okay. So now all dopant atoms are fully ionized, so that P is equal to Na. And now the equation for resistivity is this, and P is much higher than N, so you can ignore this term, and you're gonna calculate the resistivity from P mu P. So Q is 1.6 times 10 to the minus 19, and P is 10 to the 16, and mobility is where did we get this number? You know this one, Na plus Nd mobility, and this plot, right? So now watch out, Na plus Nd, but in this case Nd is 0. Okay, so 10 to the 16, you can read out the whole mobility, that is 450. So plug in all the value and take a inverse, value of it, then you're gonna get 1.4 ohm centimeter. And now let's switch the gears slightly, and what if we have additionally doped the same silicon sample of previous example, and here doped additionally with what? With a 10 to the 17 arsenide. So originally it was p-type silicon sample with a 10 to the 16 boron, but now 10 times higher arsenic donors has been included. Then what is its resistivity? Here acceptor is 10 to the 16, but donor is now 10 to the 17. So ND is much higher than NA. Whenever I'm saying much higher means at least 10 times higher. Okay. Again, whenever I'm saying something is much higher than the others, which means at least 10 times higher. The 10 times difference should be there. Okay, so here ND is much higher than Na, so now the silicon sample it becomes anti-material. So when estimating the electron concentration, N is governed by net dopant concentration. So here in ND minus Na, so 10 to the 17 minus 10 to the 16, which means that is 10 times 10 to the 16 minus 10 to the 16, so 10 minus 1 times, okay, so 9 times 16. Then using a mass action law, N times P, at equilibrium, the electron concentration, hole concentration, its multiplication is constant as Ni squared, that is 10 to the 10 squared. So since you know this number, right, electron concentration at the thermal equilibrium and not is 9 times 10 to the 16, and you know this number 10 to the 20, so you're gonna get this number. Okay, so resistivity of this sample is this, and in this case watch out that N and Q is not very different, so we should include everything. Is it right? No, still the ND is 10 times higher than NA, so just ignore A1 whole terms because it is too small. P is much smaller than N. Take a look at here, 16, 3. So just ignore this term, okay? All right. Then plug in the Q value and N value, mu value. So to get this number, watch out that x-axis indicates Na plus Nd, that is mobility. Okay, so here is Na plus Nd. So when you are read out the value in this plot, Na is 10 to the 16, Nd is 10 to the 17. So 1.1 times 10 to the 17, this point. Some student has made a mistake. This is 17, 16, so just ignore. So when read out the mobility value, he or she can read out at 10 to the 17. That is wrong. We should consider, take into account total number of dopant atoms. So 1.1 times 10 to the 17. Instead of 10 to the 17, you should read out 1.1 times 10 to the 17 here. This mobility value should be plug in here, mu n. Okay, then you're gonna end up with a resistivity value. Okay, this is a kind of homework, so please solve this example by yourself. It is much easy question, and I guess let me stop here. And if you have any questions, please review all the materials that we have learned in this movie clip and read all the associated chapters in textbook, and be ready to take a listen of next movie clips. And again, the official announcement is homework 1 and homework 2 are posted at iCampus. So solve all the problem sets and make your own answer sheet and scan it in a PDF file and upload your answer sheet at iCampus. Then my TA and I will grade your homework. Okay. All right. Thanks.